Welcome, eighth graders, to the Dallas Independent School District STEM Environmental Education Center. And we'd like to give a special welcome today to the students at Foster Middle School. Thank you so much for joining us this afternoon. We wish you could be here in person, but we're going to do our best to make you feel like you're here during a virtual field trip today. If you are watching this and have not registered for today's field trip yet, you can still do that by going to www.tiny.cc/EEC register. Once you get there, you can get yourself or your class registered for this field trip. We just use that information for our attendance purposes. And today's field trip is going to be about force and motion. During this virtual field trip, students will observe how unbalanced forces change the speed or direction of an object's motion. Students will also differentiate between speed, velocity, and acceleration. So we're going to start off today by differentiating between speed, velocity, and acceleration with Ms. Nash. Next, you're going to see me do a magnet investigation that shows how unbalanced forces can change the speed or direction of an object's motion. Third, we're going to look at forces and vectors with Mrs. Fuller. And last, we're going to see force and motion in action in the wild with Ms. Ramirez. While we're doing all of that, you can ask us questions, and we encourage you to ask questions. But since this is a virtual field trip, the way you ask a question is by going to www.tiny.cc/EEC-question-answer. And once you get there, you fill out a super short form to submit any question you have about force and motion to us. You can ask as many questions as you like, and we will do our best to answer all of them in the time that we have with you this morning. So let me stop sharing my screen here and turn it over to Ms. Nash, who's going to get us started off with speed, velocity, and acceleration.
Welcome to my classroom. Today we're talking about speed, velocity, and acceleration. And the confusing thing, at least for me, I'm easily confused, is that in everyday speech, we use those terms kind of interchangeably. Okay. You might say you're speeding, you're accelerating, your velocity, like the velociraptor. But today, we're using them in physics terms, and they don't exactly mean the same thing. So speed is the one that kind of, we do know what that means. Speed measures how fast something is moving. And speed is what we call a scalar, a weird word, scalar quantity. I think of that as like the scale. Step on the scale to say how much I've gained, how much weight I've gained over Thanksgiving. So scalar quantities only have a magnitude, how much or how little, a magnitude. Now velocity has a direction and speed. Acceleration is the rate of change of velocity, and those are what we call vector quantities. They have magnitude and direction. So I've tried to remember that one because we can say a mosquito is a disease vector. You may have heard that term. So they carry malaria from one animal to another, from one person to another. They're a vector. They move things around. It goes in one direction or another. So those are two words to remember, vector and scalar. Now, let's look at speed and velocity first. And this one, I'm thinking of how the crow flies. You may have heard that term. So we think of how the crow flies straight. They don't have to go on the road. They can fly. So if we're out in the woods and we're gonna walk from point A to point B, we're gonna go from east to west, and it's 40 meters. That's how far we're walking. But if we were, that's how far we're going, if we could fly. But we can't fly. So we have to walk on the trail out in the forest. And it has to go around that big tree and around the big rock and another big tree, another big rock. And by the time we've gotten from A to B, we've actually walked 100 meters. Because we had to make a 60 path. Yeah. So it took us 10 seconds. We were going really fast. These are imaginary numbers because they're easy to divide. So 100 meters in 10 seconds. So as we remember from our so speed is distance divided by time. We all remember that. That's easy. So distance divided by time, we get 10 meters per second. However, that crow flew really fast too, 40 meters in 10 seconds. So the velocity here is 40 divided by 10. So 4 meters per second west. Okay, you have to add that direction. So our speed, 10 meters per second, doesn't matter what direction we're going. Velocity, 4 meters per second west. It does matter what direction we're going. Yeah, so we can think about that in my little demonstration here. So I've got a ramp. See if you can see our ramp there. It's about a meter long. I've got a ball. I'm going to roll it down. We can imagine the speed. We don't know what it is, maybe 1 meter per second, let's say. So that's its speed. It's 1 meter to the second, 1 meter. But now I've got my little tray here, and it actually measures the same distance. It's a meter around, more or less. If I take my ball here, I start here. I'm going to roll it around. Roll it around. Let's do it just one time. So it goes around one time. It rolled 1 meter, but it ended up in the same place. It made a circle. So when it doesn't matter how fast it's going, it ends up in a circle, no matter how fast it's going, the velocity will be 0. Because it did not go in any direction, it just came back around. Okay. Now, acceleration is the rate of change of velocity. For instance, if I start here with my ball, it's at 0. If it ends up down here going fast at 10 meters per second, the way I calculate my acceleration is I take v minus u over time. So 10 meters per second minus 0 meters per second over 5. I like to use numbers, so 10 over 5, and I get 2 meters per second. And then squared. So the acceleration is 2 meters per second squared. So for instance, if I took my ball, I rolled it down my ramp to my tray. I'm losing all my balls. So when it changed, then direction, then it would change its acceleration, because the direction would have changed. I'm going to try to show a quick video here of a little friend of mine who's going to show us how these things happen in real life. Let me see if I can get her to find where this is. Okay, and share my screen and see if I can share it. You're sharing, not that one. Oh, there. Okay, so here's our puppy out in the backyard. So it's a Labrador Retriever. She loves to chase that ball, but watch what happens. So here we go. There she goes. She chases it. She changes direction, picks it up again. So her speed is changing, her direction is changing. She's coming back more or less to the same spot. But you can see there's lots of changes in speed, in direction. And so we could try to calculate all that, but we need some kind of a special radar gun to figure out what she's doing. And she comes back more or less to the same point. So her velocity was near 0. Okay, I'll stop sharing now. And I'm going to turn it over to Mr. Broughton for any questions.
Thank you, Ms. Nash. The question that came in was, if something is slowing down, is that accelerating? And yes, remember, acceleration happens anytime the object's speed or direction changes. But sometimes they can refer to an object slowing down as negative acceleration. So if it's speeding up, it's positive acceleration. If it's slowing down, it is negative acceleration. All right, now I'm going to share my screen with you, and we're going to get started with that investigation using some magnets. So again, unbalanced forces change the speed or direction of an object's motion. So these forces can include a push, like if you go to the grocery store and get a cart and push it around to get your groceries, you are changing that speed and direction of the cart. So those are unbalanced forces that are making that cart move, and you're the one exerting the push on it. If you pull a wagon around, you're changing that wagon's speed and direction wherever you walk. So that's again unbalanced forces changing the speed or direction of a wagon. If you throw something up, gravity is going to pull it down until it hits the ground and stops moving, because the earth would be pushing back up on that object then and not letting it go through the earth. So gravity can be an unbalanced force. Friction is an unbalanced force. The force of friction helps you start moving and stop moving. So we need friction to not be slipping and sliding all over the place. And last but not least, magnetism is another force that can change the speed or direction of an object's motion. And that's what I'm going to try to do today, is do a little investigation using some magnets and a steel ball bearing. So I'm going to take a ball bearing and try to roll it down a little ramp, and get it just close enough to the first magnet that the magnet will make that ball curve to the left, change its direction, but yet fast enough that it won't get stuck to that magnet and it'll make it past because of gravity, and then move to the next magnet and get pulled back to the right by that magnet, but still moving fast enough that gravity allows it to move on to that third magnet and go past that. And I kind of just using my imagination, it's like a little game where this is a space probe and it's flying through space, and I've got to take some pictures of this first planet. So, and planets have gravity. In real life, I got to use magnets that have the magnetic force, but fly past this one onto the second planet and take some pictures, and fly past this one, kind of using the planet's gravity, or really its magnetism, to view these three different planets. But before I do that, I did a little research, and this little video shows how a ball acts moving down a ramp, and it discusses the ball's speed, and acceleration, and I forget the third one, but the video will show us. So here we go.
A ball rolling down a long incline will be used to show how position, velocity, and acceleration of the ball change as it moves down the incline. 5 lights arranged along the length of the track flash simultaneously once per second. As the ball rolls down, it is directly above each of the lights just as they flash. This gives us a record of the positions of the ball at 1 second intervals. This is how far the ball traveled in the first second. This is how far the ball traveled in the first 2 seconds. 3 seconds. 4 seconds. We will move this distance up to a graph to keep track of position versus time. Does position change linearly over time? Next, we will graph the average velocity of the ball during 5 different intervals to see how velocity varies as the ball rolls down the incline. The ball moved this far during the first second. It moved this far during the next second. This far during the third second. The fourth second. This gives us a graph of the velocity of the ball over time. Does velocity increase linearly? Now we will graph the changes in velocity versus time by graphing the differences in successive velocities. What does this tell us about the acceleration of the ball? The acceleration is constant. A ball rolling.
There we go. So here's again are those graphs, but not overlapping each other. So you can see when a ball rolls down a ramp, it's going faster and faster as it moves down that ramp, so that you can see that the distance it travels increases non-linearly or exponentially as it moves down that ramp. Its velocity increases linearly, So it's constantly increasing in velocity as it goes down that ramp, and the acceleration stays constant. It's accelerating at a constant, or it's constantly accelerating, but not speeding up or slower. The acceleration is not increasing or decreasing. It just stays constant as a ball moves down the ramp. So that helped me kind of figure out how to set up my experiment here. So I'm going to stop sharing this screen and start sharing my iPad screen. And hopefully I can get this to work here. There we go. Okay, I think you can see my iPad now. So here's I cleared off a little space on my desk, and I just put a kind of a white piece of cardboard here. I put my magnets out, tried to space them on as best I could, and I've got a little notebook underneath one end of my piece of white cardboard to make it a little bit of an incline. Here is my ball bearing that's made of steel, so it's going to be attracted to the magnet. You can see that if I roll it into that magnet there, it sticks. And this index card is just to help me roll the ball down the ramp and aim it a little better. It seems so easy in my mind when I thought about doing this investigation that I would get the ball to roll past these magnets, and it's harder than it looks. So I'm going to place this up here so that you can see. There we go. The 3 magnets. And I'm going to put this ball on here and try to roll it past the magnets to get it to go past all 3, going to the right and then the left and then the right of the magnets. And that was an unsuccessful attempt. It stuck to the magnet. Also unsuccessful. It didn't go to the left. Ooh, that was close. At least it went around to the left-hand side of that second magnet. Nope. And no, again, and actually I'm going to give up now because it's difficult. I recorded some attempts. So let me go back to my presentation here and I'll show you my recorded attempts so you could actually see something worth looking at. Okay, so there's those graphs. And here are my attempts at doing this. So these first ones are going to be unsuccessful attempts as well. I don't know how many times I tried this over the period of days getting ready for this virtual field trip, but there were lots and lots of failures. So to think about the game, I crashed into the planets many times or just went off into space like that attempt. But you can see when you get too close to the magnet, it definitely changes the direction of that steel ball bearing because of the magnetic force. And if it doesn't get close enough to the magnet, gravity just pulls it down the ramp. So I think here's some better attempts. So there, it sent it way left. It got in that magnetic pull there, but it's just not getting close enough to the second one, but getting closer. Almost. Oof, that was close again. Well, that was all kind of almost one. Nope, flew off into space. And there, I finally got it to go past the 2 like it's supposed to, where it curved to the left and then to the right and got past that third one. So at the end, I finally did it right once. So those are, I got one more slide to show here. That was just kind of a model, but in real life, astronauts do use gravity assist when they fly rockets and probes into space. So If you want an object to lose some speed and also curve to the right, you can fly it in front of, let's say this is our moon, and the moon's gravity will cause it to curve, and then also the direction of the moon's orbit around Earth will cause that probe or whatever you're flying past the moon to lose speed. Or if you want it to curve left and gain speed, you can fly it on this side and the gravity will kind of slingshot it forward. So we do use gravity assist for real in space, although NASA would have to do many tests on land before just flying the thing out like me rolling that marble. We can't crash over and over again, or that would be way too expensive. So that is how unbalanced forces can change the speed or direction of an object. Now we're going to look at forces and vectors with Mrs. Fuller.
Hi, boys and girls. We're going to be talking about forces and vectors. And a force is a pull or push, and all forces have two properties, direction and magnitude, how big it is, its size. So forces are vectors, and a force is a vector, and two forces of equal magnitude and opposite direction will cancel each other out. Vectors, not like I just said, vectors have both size and direction. So let's look at this concept of a net force. Okay, so a net force is defined as the sum of all the forces acting on an object. And a net force can accelerate, you got that word from Ms. Nash, a mass. So we're gonna use this rock as our demonstration here. And it's gonna have 4 forces working on it. Okay, now force is measured by something called a Newton, named after Isaac Newton, our friend from the last plague, actually several plagues ago. And one of the things that we need to point out is when we have a diagram of forces, they're designated in the diagram in the form of arrows. So I'm going to show you this. A big arrow designates a big force. This one's 5 newtons. Here's one that's 3 newtons. You can see it's significantly shorter than the 5. Here's one that's 2 newtons. It's significantly smaller than the 3 newtons. So remember, a newton is the unit that we use to describe the magnitude, how big it is of a force. So an unbalanced force acting on an object causes it to accelerate. The bigger the unbalanced force, the greater the acceleration. But the more mass the object has, the more inclined it is to resist any change. So let's look at this rock. So what are the forces acting on this rock? Well, first of all, you've got the table, which is supporting the rock. So that would be, let's give it a designation of 5 newtons. So we're going to put this right here. We've got 5 newtons supporting the rock. But because we're here on planet Earth, it also has gravity on it. And we're going to designate that as 5 newtons also. We know it's balanced because the rock is not floating up in the air and into outer space, and yet is also not crashing into the Earth and going to the core of the Earth. So it's balanced, so it stays there. So I'm going to push on this side a little bit, but nothing's happening. I'm not putting a lot of force on there. I'm only putting 2 newtons of force on there, but nothing's happening. Well, why not? Well, because we've got another force pushing the opposite way, and that would be friction. Our friend friction, the thing that Mr. Broughton just pointed out. We need friction to make the bike go, and we need friction to make the bike stop. So we've got friction over here. So we've got 4 forces. We've got the support of the table. We've got gravity pulling down. We've got my effort to push it. And then we've got the force of friction resisting it. So it's not moving. So what do I have to do? All the forces are balanced. So I need to put an unbalanced force on it in order for it to move. So we're going to make my effort a little bit more stringent here, a little bit larger. So I'm going to push it at 3 newtons to overcome friction. So there it is. So that was the unbalanced force. The increase of my effort produced that unbalanced force. Now, all the forces put together are what we call a net force. And the net force is defined as the sum of all the forces acting on an object. And it can accelerate a mass, but the greater the mass, the more it resists change, right? All right. Now, what we just demonstrated here with the rock that's not moving is inertia. Newton's first law, an object at rest tends to remain at rest unless acted upon by an outside net force. All right. Now, his second law of motion is force equals mass times acceleration. The bigger the force, the bigger the acceleration. I didn't put a big force on it, just 1 Newton's worth greater than friction. So I just moved it a little bit and it resisted me. The more mass it has, this pretty big piece of obsidian, the more resistance to any change in motion. All right, so let's put the obsidian down and look at forces in a different way. Let's look at a teeter-totter. Now, when you go to the park with your family, you might get on a seesaw or a teeter-totter. So you get at one end and a family member gets at the other, and what happens? Well, the one that has the heaviest person, that end goes down and the other end goes up. So that's an unbalanced force. This is heavier than this. So how do you make the forces balanced? You have the heavy cousin or the heavy aunt or the heavy parent move closer to the fulcrum. That's the pivot, the center part right there. So the little person stays at the end and the big one moves to the end and the forces are then balanced. So a seesaw or a teeter-totter is a first-class lever. Remember Archimedes when he said, give me a big enough lever and a place to stand and I can move the world. This is a simple machine, but it's a very useful simple machine. Scissors are levers. They're first-class levers. A crowbar is. So we can get a lot of work done with these. Now, the last thing I want to talk to you about unbalanced forces and vectors and things like that would be when you think about electricity, when you think about people that wire things, they have to use a certain gauge of wire. So I've got 2 gauges of wire. I've got a little bitty skinny wire right here, and I've got a big fat wire right here. Well, it's measured by the gauge, how big around the wire is. If you don't use the correct gauge, the correct thickness of the wire, the electricity won't flow all the way through. So it becomes unbalanced it doesn't do the job that you need for it to do. So if you have any more questions about forces and vectors, Mr. Broughton will be glad to answer those. Thank you.
Thank you, Mrs. Fuller. The question that came in was regarding the arrows to show vectors. And then the question is, does the length of the arrows matter? And yes, in that a larger force should have a larger arrow and a smaller force should have a smaller arrow. But like in the example, it's not that you have to get out a ruler and measure 5 inches for an arrow that represents 5 newtons and 2 inches for an arrow that represents 2 newtons. You just want to make sure that this smaller arrow represents a smaller force and a larger arrow represents a smaller force, and that arrow is pointing in the correct direction that the force is pushing or pulling or exerting in the whatever direction that it is. So I hope that answers that question. Now we are going to see speed and velocity in the wild with Ms. Ramirez.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be talking about average speed of some of our farm animals. So essentially, average speed is just the total distance traveled divided by the total time. So super easy equation for average speed, and the units for average speed, scientists and most of the world use the metric system. So the units for average speed will be in meters per second or kilometers per hour, or if it's a short distance, we can use centimeters or millimeters. Now here in the US, we use the customary system. So if you've ever driven a car, you know that your average speed is going to be in miles per hour, but we can also use feet per hour. And if it's a small distance, we can again use inches and then seconds as well. But again, since we are scientists, we're going to be using the metric system today. And the way we're going to do it, we're going to be looking at a couple of videos of average speed for some farm animals, and then we have an animal guest that we're going to be meeting later on. So I'm going to go ahead and share my screen with you guys so we can start the presentation. And the first animal we are going to take a look at will be cattle. So cattle have an average speed of about 15 miles per hour. Now, again, since we said that we are scientists and we're going to be using the metric system, think of how can we convert miles per hour to kilometers per hour. So the conversion for that is easy. So 1 mile is equal to 1.6 kilometers. So if we want to convert that 15 miles per hour into kilometers per hour, all we have to do is multiply. So if you look on the bottom of our PowerPoint, all we're going to do is take that 15 miles and multiply it by 1.6 kilometers, and that gives us about 24 kilometers. So in other words, the cow has an average speed of about 24 kilometers per hour. So I'm going to go ahead and show you that little video of some cattle running. It's going to be in slow motion so that you can see it better. But while you guys are watching this cow run, some super quick facts. Cattle have panoramic vision, and all that means is that they can see almost all the way around their head. But they have really bad depth perception. So they can't really tell if something is super close to them or if it's super far. So that's why it's never a good idea to stand or approach cattle from the sides, because they can't really tell if you are close enough or if you're far enough to be determined if you're a threat or not. So you don't want to spook them. And then on the right, we have a picture of some of our cattle, Sarah and Oreo. And so technically speaking, it is a calf if it is 1 year or younger. It's a bull if it is an intact male. It's a steer if it is a neutered male. And it's a heifer if it is a female that hasn't had any calves yet. So I know typically everyone just calls everything a cow, but there is a difference between the different names. And then the next animal we're going to take a look at are goats. Goats have an average speed of about 10 to 14 miles per hour. So not quite as fast as our cattle. But again, see if you can convert 10 or 14 miles per hour into kilometers per hour using the conversion below. And then while you guys are doing that, we'll play a little video of some goats running. Unfortunately, we don't have these kinds of goats here at the Environmental Center, but they are super cute to watch. Let's see if the video is going to load. If it doesn't load, let's see. We've been having internet, there it goes. These are little dwarf goats. Again, we don't have this kind, but I sure wish we did. So they are super cute. Maybe one day we'll get some of those goats. But the goats that we do have at the Environmental Center, we only have one. His name is Jabez, and he's a boar goat. Boar goats are bred for meat. We don't eat any of the animals we have here at the Environmental Center. We use them as our pets and for teaching with. But you can see that Jabez here is eating some leaves, I think from a red bud tree. He's generally a pretty good goat, but he does like to headbutt people sometimes. So that's goats. Our next animals are chickens, and we do have chickens here at the Environmental Center. We have lots of them. So the video that you're going to see here are chickens that we have at the Environmental Center. This video was taken in our parking lot. We have a variety of different breeds of chickens. And then you should be able to see our turkey, Mr. Gobbles. And then in a little bit, you'll see a little weird chicken. His name is Flash, and he sure can run fast. He stands out apart from all the other chickens just because he looks so unique. But chickens are prey animals. We have lots of predators out here at the Environmental Center that would love to eat them. We have hawks, we have bobcats, coyotes, even some snakes. So they do have adaptations that allow them to escape predators, and running is one of them. So that's the chickens. And then just a little infographic for you guys. On the left, we have a picture of the Olympic winner for sprinting, and that's Usain Bolt. And he had a record of 27.8 miles per hour for sprinting. So that's actually really fast if you compare it to some of our other animals on the diagram. So the average fit person can run about 8 to 10 miles per hour. A T-Rex could run about 25 miles per hour. So theoretically, Usain Bolt could outrun a T-Rex. Now, given this is for sprinting, so short distances, but he is still super fast. And then this next video is of Pepper. She's my blue silky chicken, and I recorded her running down my classroom. So as you're watching the video, be thinking about how can you describe Pepper's change in position and her speed. So I know you don't have exact measurements for speed, but you can still describe speed in terms of slow, fast, medium. Also be thinking about how can you tell she's even moving. So pick a reference point in the video. And then did Pepper get faster, slow down? Did she stop at any point in the video? And just for your reference, she ran about 16 feet in 15 seconds. So think about how can you describe her average speed and her velocity. And just so you know, each square on my floor is 1 foot. So that's how I know she went 16 feet and she was running in the southern direction. So here's the video of Pepper. She's a blue silky chicken. I've had her for over 5 years. She can run faster than that. She usually runs pretty fast when she gets spooked, but she's eating her favorite treat, which are dried mealworms. And then just a little sample math problem using Pepper. So Pepper ran 16 feet in 15 seconds. So my question for y'all is, how can we calculate her average speed in meters per second? So your conversion is 1 foot is equal to 0.3048 meters. So think really quickly, how could you solve question number 1? And I'm gonna walk through it with you guys. So the first thing you need to do is convert feet to meters. And all you have to do is multiply. So you're just gonna take that 16 feet and multiply it by your conversion, which is 0.3048 meters. And that will give you about 4.88 meters. So she ran 4.88 meters in about 15 seconds. Next, we need to figure out how many meters she ran per second. So all you have to do is divide. So we're going to take that 4.88 meters and divide it by her time, which was 15 seconds. And that gives us 0.32 meters per second. So that is her average speed. Now, question 2 says, how long will it take her to run 15 meters? So think really quickly, how could you set up your equation to solve that? So given that her average speed is 0.32 meters per second, all you have to do is divide. So you're going to take that 15 meters and divide it by her average speed, which was 0.32 meters per second. And that will give us a time of 46.875 seconds. So theoretically, if she kept that constant speed, it shouldn't take her that long to run the 15 meters. And that's about the approximate length of my classroom. And an easy way for you guys to remember your formulas and whether you're going to divide or multiply is just to create a simple triangle. So if you have a word problem, all you're going to do is just draw a triangle on your paper. And then if you remember the saying, duh, slow turtle, and I know it sounds kind of slang, but it really does help you remember. So you have your triangle drawn, and then duh, slow turtle is written inside it. Duh stands for distance, slow stands for speed, and turtle stands for time. So the way the triangle method works is, if you don't know your distance, then what you're going to do is you're going to multiply speed multiplied by your time, and that will give you your distance. If you don't know your time, all you're going to do is do distance divided by speed. And then if you don't know your speed, all you're going to do is do your distance divided by time. So that's a quick and easy way to remember whether you're dividing or multiplying. And then my challenge question for you guys, I walked 2.8 miles in 45 minutes. What is my average speed in kilometers per hour? So your conversions that you'll need for this question, 1 mile is 1.6 kilometers, and of course 60 minutes is 1 hour. So something cool that you guys can use, there's a free app called Map My Walk. So you can download it on your phones, and it uses your cell phone's GPS to track where you went, and it gives you your average speed, your distance, your pacing. So the map that you see here on this slide is from that app. So if I look at that picture right here, that satellite image, my question for y'all is, what is my displacement? So think about what that word means. What is my displacement if I end at the same place I started? And then just do really quickly, write down the question or take a picture with your phone so you can try and answer it later. But since y'all aren't able to visit us, I went ahead and did a little video of some of the things I saw on my nature walk. So I am going to show you that video. Let me just minimize my PowerPoint really quick. And then we will move on with the video. If I'm quiet, you might hear the birds. This was taken before Thanksgiving. So you can see all of our deciduous trees have lost their leaves for the most part. It was a windy day, so think about what science tools can we use to measure wind speed. I am a loud walker, so the leaves are definitely very crunchy. Those are Osage orange. People call them horse apples. What do you think used to be in that empty field right there? And this was a cool snake that I happened to come across. He kind of stood out, didn't really camouflage in with those brown leaves. But we do have all sorts of wildlife out here. I've come across skunks and even deer during one of my walks in the morning. All sorts of cool creatures out here. So I'm going to go ahead and stop the video, and I'm going to stop the screen share. And then before you guys go, since we saw Pepper in the video, I'm going to go ahead and bring her out for you guys to see. So this is Pepper. She's a blue silky chicken, and they get that name because if you were able to touch her, she feels really soft like silk. And she actually has these blue ear patches on her skin. So hence the name Blue Silky Chicken. And she's been here with us for over 5 years. She's probably one of the best pets I've ever had. She is an omnivore, so she eats a variety of insects, but also plant material as well. So I'm going to go ahead and put her up. And that's all I have for you guys today for average speed. We're going to go ahead and pass it back to Mr. Broughton, and he's going to answer any questions.
Thank you, Mr. Ramirez. The question that came up was, what is the fastest animal you have out at your center? And I would say the fastest animal would be our hawks. We don't have any pet hawks, but they do live here. They're in the wild. Some hawks can fly as fast as 120 miles per hour. I'm not sure if our hawks are that fast, but they can really fly through the sky pretty fast. If you wanted to go with land animals, then I would say the white-tailed deer. A white-tailed deer can run up to 30 miles per hour, which is fast for the animals around here. I don't think there's anything faster than white-tailed deer here at our Environmental Education Center or the Post Oak Preserve Forest. All right, now I'm going to share my screen with you to do a quick recap of what we did today. So again, today's field trip was all about force and motion. During this virtual field trip, students observed how unbalanced forces change the speed or direction of an object's motion, and students differentiated between speed, velocity, and acceleration. So we started off this field trip by differentiating between speed, velocity, and acceleration with Miss Nash. Second, you saw me do the magnet investigation to show how unbalanced forces can change the speed or direction of an object's motion. Third, we observed forces and vectors with Mrs. Fuller. And you just saw force in motion in the wild with Mr. Ramirez. Thank you so much for joining us this afternoon. We appreciate you taking the time to learn about force in motion with us. We hope you can join us again next time. It'll be after the winter break. And the next field trip for 8th graders is Newton's Laws. We would appreciate you letting us know what you thought about today's field trip, and you can let us know by going to www.tiny.cc/EEC feedback and filling out a short feedback form for us. Have a great rest of your day, and we'll see you next time. Goodbye.